Hi everyone, this is Sajad Moslehi. In this video, I'm going to simulate the capillary transition zone in oil reservoirs which exists between the aquifer and the oil zone of the reservoir. These are the final pictures of the simulation and we will get to this at the end of this video. Alright, let's go through the code. These first three lines are to make sure that the command window and the workspace are clear and all the figures, if any, are closed. Let's start the main part of the code, which is the construction of the model. First of all, we need to construct the geometry of the reservoir. The cell dimensions, actually we want our reservoir to have 20 cells in the X direction, 20 cells in the Y direction, and 20 cells in the Z direction. And we want the physical dimensions to be 100 meters. Actually, the length of the reservoir, 100 meters in the X direction, 100 meters in the Y direction, and 100 meters in the Z direction. So we have a three-dimensional reservoir to simulate this phenomenon. All right. Now it's time to introduce these numbers to MRST. We use the function deal to distribute these numbers to these output arguments, which are the number of cells in each direction. We have also used this function to distribute the physical dimensions to the output arguments, which are the lengths of the model in each direction. And here we have used the function cardGrid to tell MRST these pieces of information. The first argument is the cell dimensions. The second argument is the physical dimensions. All right. Now it's time to see what the reservoir looks like using the function plotGrid. At the end, of course, we don't need this function to see the reservoir. Actually, we have used this function to calculate some additional parameters of the cells that we have, like the centroids of the cells, the volumes of the cells, etc. Let me run this section of the code. Actually, we use this these additional data, in the next parts of the code. Now you can see, the grid, and actually, as you see, it is a three-dimensional reservoir, a three-dimensional grid. All right. Let's go to the next part of the code, and we're here going to determine the rock properties. A reservoir is heterogeneous and also isotropic heterogeneous because we want a reservoir, actually the permeability of the reservoir, to vary from 1 millidarcy in the west to 400 millidarcies in the east of the reservoir, and it has a linear relationship. All right. Then let me talk about this a little bit. The porosity of the cells are equal to 0.2 or 20%, and actually the properties are isotropic because the permeability in all directions are the same. So here we have defined the permeability only in one direction, and we have used the function repmat to repeat this matrix, this row vector, in the other two dimensions to define these numbers for all the cells of the model. All right, we have used the function makeRock to introduce these data to MRST. the first input argument is the grid data structure. The second input argument is the amount of permeability of the cells, and the third input argument is the porosity. Alright, now it's time to see the permeability values on the cells of the reservoir. And as you see here, in the west of the reservoir, we have the lowest amount of permeability, and in the east of the reservoir, we have the highest amount of permeability, and actually this permeability linearly changes from west to east, or linearly increases. All right. Here we have computed the half transmissibilities of the reservoir, and now it's time to define the fluid properties. The water viscosity is 1 centipoise, oil viscosity 5 centipoise, the water density 1,000 kilograms per cubic meters, oil density is 700 kilograms per cubic meters, and we have used the simplified Brooks and Corey model with its exponents equal to 2 and 2 for both of the fluids, and actually, as you know, actually Brooks and Corey model actually is used to calculate the relative permeabilities of the fluids that we have. Here we have used the simplified Leverett J function to calculate the capillary pressure, and actually this is the simplified version of the function. Alright, and this is actually the most important part of this program, because we want to consider the effect of capillary pressure on our reservoir and on the flow of the fluids that we have in the reservoir. We have considered the effect of gravity, and we've used the function in its simple fluid jfunc because this function considers the effect of capillary pressure. The first two input arguments are to determine the viscosities of the fluids that we have, the densities, the Corey exponents, the surface tension that exists between the two fluids that we have, in this case is 50 dynes per centimeter, and at the end we have specified the rock data structure. Why has it been specified here? Because we have porosity and permeability of the rock in this equation, so we need to put this information to this function to calculate the capillary pressure. Alright. Here we have specified the initial conditions of the reservoir. Actually, the reservoir is initially 100 bars, actually the pressure of the reservoir. And here we have, we want a reservoir, actually the top of the reservoir to be, saturated with oil, and the bottom half of the reservoir to be saturated with water, and here we have done that. Alright, the total simulation time is 5 years, and here we have used this method to determine the time steps that we need to have, and actually as you see, these time steps are not the same. Some of the first time steps are different, and actually it increases at the beginning, and after a while it will get constant. And we've done this to make sure that our solution is going to be stable. And that's it. Now we have used actually the main functions of the code, which are incomp TPFA and implicit transport, which I've already talked about, and actually do the main calculation of the reservoir and are the most computationally intensive part of the code. Alright, and we've used this function plot cell data to see the changes. And actually, this simulation, actually this is the simulation of this code. But because it's very slow, I've already done that, and you can see the video of the simulation here. And as you see, the water actually, the reservoir rock is water wet. So, water is going up, especially in this part of the reservoir because it has the lowest amount of permeability. And so, the water increases more, actually, goes up more at this part of the reservoir. But in this part, because the permeability is very high, the water doesn't go up as much as it does in this part of the reservoir. So let me show you the video again from the beginning, and the time is shown here. And that's it. This is what we're going to do, and I hope you enjoyed this simulation. Thank you very much, everybody. Hope you're having a great time.